All right. Gentlemen, yesterday we just made a very short introduction to this course, and we talk about our evaluation system and the course goals and what is it? The first part of the first chapter. It was about vectors, right? And the definition of a vector and addition on vectors and subtraction and the things. So today we will continue with the second part of this chapter, that is the length and angle, the dot product. Two important things. Okay, we will talk about these two basic concepts and do some problems related to these concepts. And if we have time, we will talk about lines and planes. And maybe on Friday, we will talk about applications. That's it. So what we have here, we are going to actually review, or let's say study, the dot product, length, the Cauchy-Schwarz inequality, that we are going to use this in a lot of proofs, the triangle inequality, and there's the same thing, distance. Distance means how do you find the distance between two vectors, actually, or 2 points here, actual vectors, orthogonal vectors. You will see the condition when actually two vectors are orthogonal to each other. And the projections, the projection of one vector onto another vector. And later we will see that the projections of vectors on a plane and these things. Let's start with the dot products. Okay. Here, if we are given two vectors, u and v. So now we are just considering the general case. As you see from here we are given two vectors. That means that vector u and vector v from where? N-dimensional space. That means that they have n components, or they are specified by n components. If n equals 2, we know that it is just, what is it? Two-dimensional space. If it is 1, it's only on the line, right? For example, let's say if n equals 1, later we understand more and more about this space. So that means that everything is on a line. How about if n equals 2? That means that now here we have two components, and vectors are here. They are living in two-dimensional space. That is the first component, x sub 1. That is the second component. But here we have only one component. And how about if n equals 3? Now here we have three different components, right? That means that these vectors are living in three-dimensional space. That is the first, second, and third. And the starting from here, let's say that is x sub 1. This one is x sub 2, and this one is x sub 3. Okay. So here we are introducing new concept, the dot products. What is a dot product? As you see, dot product is, the dot product of two vectors. Okay, the dot product of two vectors. We don't have the dot product of 3 or 4 vectors. We have only the dot product of two vectors from the same space. That is defined as, what is it? The sum of the product of their corresponding components. As you see here, the first component is multiplied by the first component, plus the second component is multiplied by the second component, and the last and nth component is multiplied by the nth component. Okay, this is just a definition. It's like compact notation of this operation. And you may wonder why we have to introduce this. You will see that in a lot of times we will have something like this. Okay, this thing appears. Okay, this appear in a lot of applications, in problems. That's why the mathematicians thought that we need to introduce something so that we can describe this thing in very compact form. That actually these mathematicians did do this a lot in math, because you will see that something appears very frequently and its appearance is a bit huge, or it's not in compact form, so they introduce something new. So that is something like that. That is dot product. Okay, so for example, immediately if you're given two vectors, let's say the first vector is here, let's say 1, 2, 3. and here we have dot, the second vector, let's say 4, 0, 1, for example. What is the dot product of these two vectors? That is 1 times 4 plus 2 times 0 plus 3 times 1, which is equal to 4 plus 0 plus 3, that's equal to 7. As you see here, the result is scalar. It's just a real number here. Okay, so the dot product of two vectors is just a scalar. Okay, as you see here, the only thing is to represent this expression on the right hand side in a very compact form. That's why we are introducing this dot product. Example, compute u dot v when u equals this, I mean the components of vector u, 2, 3, negative 5, and components of vector v, negative 1, 0, 7. So if we compute this u dot v, that's equal to, here we have 2, 3, negative 5, dot, here we have negative 1, 0, 7, right? So we should just multiply their corresponding components and add them up. 2 times negative 1, that's negative 2, plus 3 times 0, that's equal to 0, plus negative 5 times 7, here we have negative 35, which is equal to negative 37. So the dot product of these two vectors is, what is it? Negative 37. All right, now immediately let's see some properties of these dot products. As you know, in math, first you define something, and after that, we introduce some properties, or we just obtain some properties because we have to know what properties does it have, right? So that we can use in solving problems. We don't have to go through a long procedure every time. So that once we prove these properties, so we can use them in solving problems or when we are dealing with any kind of problem related to vectors. So it says that let u, v, and w be vectors in Rm. That means that these three vectors are living in n-dimensional space. Right here we have a kind of n-dimensional space. This is their world, and all vectors are determined by n components. So here we have one vector. If we just pick any vector, v, and here we have w. So three vectors. Okay. And let C be a scalar. And you know what we mean by a scalar, right? It's just a real number. Our real number is 5, 3, negative 2, or 1 over 2, and a real number. The first property says that then u dot v equals v dot u. In math, we call this commutative property, right? And the second one says that associative one over addition u dot v plus w is equal to u dot v plus u dot w. In a similar way, if you just multiply u by c, we know that multiplying a vector by a scalar, that means scaling a vector. Either you're just shrinking or extending, right? So dot v, it is the same as first u dot v and multiply by c. And fourth one is important. It says that the dot product of two vectors, the dot product of two vectors, the dot product of two vectors, what is it? It is greater than or equal to. It's not two vector, it is u and u, right? The same vector. You should actually, here we have uv, uvw, but pay attention here. This one is u, this is also u. The dot product of u by itself, right, is always non-negative. That means that it is either 0 or positive. And the dot product of u and u is equal to 0 if and only if u is equal to 0. I mean, that's u is 0 vector. Guys, proof is very simple. I mean, not so difficult. How do we prove them? We can just prove them component-wise. For example, let's say the first one. Let me change a bit darker. And here n, all right, but assume that's only for, let's say, this u, v, and w. Instead of just 3, we write n. That will, but in this way, we can actually prove this for n-dimensional vector from n-dimensional space. Let's say these vectors are from a 3-dimensional space, okay? So why u dot v equals v dot u, for example? Let's say u dot v means that here we have x1, not x1, since actually vector name is u. Let's say components are also u sub 1, u sub 2, u sub 3. And here we have dot, here we have v sub 1, v sub 2, v sub 3, right? So according to the definition, how actually we define this dot product? That's equal to u1 v1. Guys, again, I hope you understand the difference here. These two things are vectors. Okay, because if I just write boldface, it gets a bit ugly. That's why from the context you understand that these are vectors, these are scalars with some script notation. Plus, here we have u sub 2, v sub 2, plus u sub 3, v sub 3. Okay. And these are just real numbers here, right? And we know that for real numbers, right, if you just pick any two real numbers, here we have any two real numbers, and we have this property that A times B equals B times A. So using that property, I can just write it as V1U1 plus V2U2 plus V3U3. And now again, if I just write this in compact form using the definition of dot product, what we have here. So actually the first components are V sub 1, V sub 2, V sub 3. So here we will have V1, V2, V3 dots. And here we have U1, U2, U3. And actually, what is this? That is just our v vector. So here we have v dot. How about this one? That's our u vector. On the left-hand side, we have u dot v. On the right-hand side, we have v dot u. So the first one is proved. And how about the second one? In similar way, you can just write this. At the time for this, what we have here, we will have something like this. If we just take any i's components, we will have like this, u sub I times, right? Here we will have this one, v sub I plus w sub I. And again, these are, what is it? These are scalars. So again, just using the properties of real numbers, I can just write it as, what is it? U sub I, V sub I, plus U sub I, W sub I. And after that, by just regrouping this, we can just write this in this form. And again, just converting this into the dot product form, I can write in this form. And also in similar way, exactly, it's just a constant, you can do that. And how about 4? Let's just do 4. And it says that if, I mean, the fourth property says that u dot u, it says always greater than or equal to 0. Okay. Why is it so? Because, again, if you just write this, u dot u, again, it's just a three-dimensional space. For n, instead of 3, just write n. It will be exactly the same for n-dimensional space. So what are the components of u in three-dimensional space? That is u sub 1, u sub 2, u sub 3. Dot, and here we have v sub 1, v sub 2, v sub 3. So simple, just v1, v2, v3. Oh, sorry. Actually, it is u. So here we have u. Here we have u. Here we have u. And the dot product, u1 times u1 plus u2 times u2 plus u3 times u3. So here we have u1 squared plus u2 squared plus u3 squared. And actually, as you see here, each term here is greater than or equal to 0 because u1, u2, u3, these are real numbers. And we know that the square of real number is always non-negative. That's the same thing. Second thing also, greater than or equal to 0. Also third thing, that means that this sum must be greater than or equal to 0. And then the second part, that is the first part. In the second part, it says that u dot u is equal to 0 if and only if, this means that if and only if, that u is a 0 vector. That is a zero vector. What does it mean, this if and only if? If u dot u is equal to 0, then u must be 0 vector. And also converse is correct. True. That means that if then u is 0 vector, then it is dot product by itself is equal to 0, right? And first, let's just prove this implication. And we have to prove that if u dot, that means that if u dot u is equal to 0, we have to show that u is a 0 vector. How do we show this? Okay. So we are proving this implication. All right. So again, what is u dot u? That's equal to, again, from here, that is u sub 1, u sub 2, u sub 3. And here we have dots. Here we have u sub 1, u sub 2, u sub 3, right? Which is equal to u sub 1 times u sub 1, u sub 1 squared, plus u sub 2 squared, plus u sub 3 squared, right? And if this thing is equal to 0, what does it mean? And we know that the first term, it is non-zero. Second term, it is non-zero. And third term is equal to non-zero, non-zero. So when the sum of non-zero numbers is equal to 0, if and only if each one is equal to 0. Otherwise, if one of them is not equal to 0, it will never be equal to 0. So this implies that u1 equals u2 equals u3, which is equal to 0. That means that our vector u is a 0 vector. And how about this implication, the converse? And we are saying that because we are saying that if and only if. In math, if and only if, this means that we are going to use more often. So that means that it is IFF. And what does it mean? That means that if and only if. Okay. What does it mean? It means that if this thing is true, then this must be true. And if this thing is true, then this must be true. Okay, it's about two different statements that they are asserting each other. And this way is quite easy, as you see, because if, that means that now we have to show that if u is a 0 vector, then it is dot product by itself is equal to 0. And since u is a 0 vector, that means that all its components are 0. So what is u dot u then? It is just 0, 0, 0, dot 0, 0, 0. And here we have, as you see here, 0 plus 0 plus 0. That is equal to 0. That is the proof of the last property. All right, let's continue. Let's see one example related to dot product. It says that prove that u plus v. Actually, you prove that u plus v, and here what is missing? It must be dots. Maybe I forgot to put dot here. Let me put dot immediately so that you don't get confused. Okay. Prove that u plus v dot u plus v is equal to u dot u, right? Plus 2 times u dot v plus v dot v. Okay. I should not actually confuse with our usual multiplication. It's similar, but not exactly the same. So we should prove this. How do you prove this? Let's use different color here. We're proving, let's say, proof. And just we are going to use the property of that's dot product. So here on the left-hand side, we have to show the left-hand side of this equation equals to the right-hand side. So from here, u plus v dot here we have u plus v. That is equal to, so one by one, I can just write it, take it as a single vector. As you see here, the second here, I'm just using the, going to use this associative property, right? That's equal to times this, times plus, times this. So using that property, if you just assume that that is a single, what is it? Vector, let's say it's w, then here we will have u plus v dot u plus u plus v dot u, and here we have v. And now I'm going to use the first property. What is the first property? That is u dot v equals v dot u, right? It's a commutative property. And using this property, I can rewrite this as u dot u plus v. That is the first part. Plus the second part is v dot u plus v. Now again, using the associative property, I can just write it as u dot u plus u dot v plus v dot u plus v dot v equals, and also we know that u dot v equals v dot u, the first property. So I can write it as u dot v plus 2 times u dot v plus, okay, here it's not v, it's u dot u. The first one is u dot u dot v dot u, that's v dot u, plus v dot v. So that is v dot v. And proved. Right now that is equal to, what is it? Left-hand side of the equation. That is here, actually, right-hand side. So since right-hand side equals left-hand side, so the thing is proved. Okay. Now let's talk about length of a vector, or sometimes we call this norm. So length or norm of a vector, v. Let's say we are given a vector from n-dimensional space. That means that this vector is living in n-dimensional space. Is the non-negative scalar. So we are saying that the length, and we know the length is always positive, non-negative. It is a non-negative scalar. It's a real number, and we define by this a couple of what vertical lines. That's v defined by this, which is, that is defined by this. The length of v, or the norm of v, is equal to square root of v dot v, and this is how we are defining this. And from here, what is it? We know how to evaluate this v dot v. That's equal to square root of v1 squared plus v2 squared plus blah 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 vn squared. And immediately, as an example, to understand this, if you just take one vector from two-dimensional space, that means that this v has components like this, right? V sub 1, v sub 2, right? That means that here it is something like this. So here we have x sub 1, the first, x sub 2. So vector v, it has this component somewhere here. So this one is v sub 1, right? This one is v sub 2. And what is the length? See here, we are just using the, what is the Pythagorean theorem? This length is v1, v2. So this square root of v1 squared plus v2 squared. And using this definition, then the norm of this vector, that is equal to v dot v. And we know how to evaluate this. That's just equal to the sum of the squares of each component, or all the components. That's equal to v1 squared plus v2 squared. Okay, gentlemen, if you have any question, anytime you may stop and ask. If you don't ask anything, I just keep teaching. Okay, don't be shy. Anyway, I cannot see your face. I don't know you, right? Maybe some of you, maybe 1 or 2 students, I know that's there, but the others, I don't know. So don't be shy. Continue. find the length of U. Find the length of U. So it is in two-dimensional space, right? Okay, let's use dark blue here. Solution. So what is the norm or length of this U? That is equal to square root of 2 squared plus 3 squared. That's equal to 4 plus 9. So that's equal to square root of 13, right? And if you're given, for example, let's say another vector, let's say whose components are -1, let's say 2, 3. Then what is the norm of this vector or the length of this vector? That is -1 squared plus 2 squared plus 3 squared, which is equal to square root of, it is 1 plus 4, 5, 5 plus 9, that's equal to 14. Okay, and if we have, let's say, another vector, let's say W, this is from four-dimensional space, 1, 0, 0, -2, for example. What is it? The norm of this vector W is equal to square root of 1 squared plus 1 is 0 squared, 0 plus 0 plus -2 squared, that is 4. So the length of this or the norm of this vector is 5. All right, so immediately we have these two properties about the length. It says that if it's a theorem, let V be a vector in n-dimensional space, that's Rn, and let C be a scalar, that's just a real number. Then the length of this V, vector V, is equal to 0 if and only if the vector is a 0 vector. When actually the length of vector V is equal to 0. If and only if is equal to 0. We have already proved this one, right? If you remember, that is the last one. It's very similar way you can prove this. This is the one, okay? The second part. So I'll just skip this. Now the second one, that sometime we are going to use this in proving some theorems. That's why you should understand this. So the length of, or the norm of C times V is equal to here, not only C, absolute value of C times V, right? And why is it so? Because here, C, here we have V, equals, what does it mean? Again, by definition, this means it is CV dot CV, right? Again, using the property of dot product, that's equal to C times C. It is C squared, this is parenthesis, okay, times, I can just write it V dot V. Again, I'm using the third property of dot product, right? So that is, I'm just using, what is it? The third property. I'm using this property here. So I can write, again, using the property of this roots, we can write it as square root of C squared times, here we have square root of V dot V. And what is square root of a number? Square root of number is always positive. Sometimes students confuse. For example, what is square root of 4? It's equal to 2. It's not equal to plus minus 2. Or square root of 16 is equal to 4. It's not plus minus 4. It's just 4. It's a single number. Okay, they confuse this with this thing. If you just solve x squared equals 16, this is different thing. This is an equation, quadratic equation. But here we have a single number. And that's why it's just equal to 4. So that means that to make sure that it is 4, because the C, it may be negative. Like, for example, let's say, what is square root of -4 squared? And -4 squared is, we know this 16. So that's equal to 4. Okay, that's why we need to write this in absolute value. Whatever C is, here we will have always positive number. Because the square, anyway, this will be positive. So that is equal to absolute value of C. And how about this square root of V dot V? Just from the definition of the length of a vector, that is equal to the norm of V. That is the proof of this property. Guys, let's have rest. Okay, 10-minute break. After that, we will continue. What time is it? It is 10:57, 11:10. We will have, the next session.